All right. I'm going to repeat the introduction really quickly because Gianni was not in the room, but we're very excited to have Gianni De Fabritiis join us today to give a talk on machine learning interatomic potentials. He's the CEO of Accelera and an ICREA research professor at the University of Pompeu-Fabra, where he leads the computational science laboratory. He founded Accelera in 2006, and in 2012, Accelera Labs, the R&D division. The mission of Accelera is to enable computable drug discovery, developing the algorithms to automate drug discovery via high throughput computations and machine learning methods. We're very excited to welcome him today, and thank you so much for being here.
Thank you. Thank you so much. Can you hear me well?
Yes, we can hear you.
Okay, thank you. All right, thank you for the introduction. I'm sorry I wasn't able to come at the last minute for a reason which had nothing to do with the summer school, but I'll be able to give the presentation online. So the topic of the presentation is about machine learning potential, and I'm gonna show you a little bit what we've been doing around the last years and point you to some of the source code and repository that we have online so that you can carry on from there. Just a little introduction because I don't know your background. So I'm actually a mathematician as a background, but I started to work on this kind of computational physics since the PhD, really. And so the question we're posing here is, we would like to be able to we would like to be able to model molecules on the left, atoms, molecules, but also like these structural elements like macromolecules, which formed by many atoms, and then assemblies of these macromolecules, and then in the cells you have all these kind of complicated structures. And while on the top, on the left, so the very small scale, physics is a good approximation that depending on the approximation you want to use. So you could just use quantum mechanics and be totally accurate, but you could have multiple approximation going from atoms to macromolecules, and then even assemblies of these macromolecules can be done with some sort of, again, more further approximation and so on. So is machine learning a good language for these things? Maybe. I'll show you today there is, at least from a point of view of simulating these entities, there is kind of a unifying framework which allows you to do that in terms of machine learning potentials. So that's a little bit the topic of the talk. So what is molecular simulation? Well, you can take atoms and then put it in space, like particle, approximated as particle, point particle, and kind of run it. And then you can have you can kind of explore phenomena like this one, where you have an SS2 domain which attached to a peptide. The peptide has a residue which is charged, and is kind of recognize this residue in the protein first, and then find this pocket find this pose into the binding pocket of this domain. This is a regulatory domain. Doesn't really matter. These simulations here, just you take the atoms of the protein, you take the atoms of the peptide, you let it go, and naturally, based on the force field that you gave, they form interaction. They form, and this interaction drive this dynamics that you're seeing here. And you'll see, like, the color says is kind of proportional to the movement. No? So you see that the peptide, once it's bound, is way more rigid than what it was when it was unbound. This has a cost in terms of free energy that you need to compensate by the interaction that you're building up in this kind of type of complex. This simulation is actually quite old. But we were one of the first group to be able to show that you could do these things by just running the parts and let it form. And we'll see how we improved from this one, which was, I don't know, many years ago, but many, to current days. Okay, so machine learning potential. So the simulation that you just saw there is based on a molecular, what we call it, molecular mechanics force field. By molecular mechanics, we mean that we are not, we're treating essentially all atoms as Newtonian particle. So the dynamics is not quantum. It's not driven by quantum mechanics. We make an approximation. We forget about the electrons somehow. We coarse grain all the electrons into a potential which applies like if there were planets kind of thing on the nuclei, so on the heavy atoms and hydrogens. And the potential that was devised many years ago is based on this formula on the right. So relatively simple. So you have the bond terms, which represent the electronic structure that you have when you have two molecules covalently bound, two atoms covalently bound, then angled, which further restraint on this movement of these three atoms. So you have two body terms in terms of bonds, three body terms in terms of atoms. Then you have four body terms in terms of torsions, where you try to move two planes across each other, or you maintain planarity, like in a ring, in a benzene ring. And then there are, and these are kind of, these first three terms are kind of heuristic. So you just want two atoms not to feel some sort of force to keep it together, which is forced by the electrons really, but we don't have electrons, so we just use this simple harmonic potential. And again, as a simple harmonic potential for the angle, no physical meaning here. And it's also for the torsions, just a way to impose these constraints. And then we have some kind of physical terms. One is Lennard-Jones potential, which kind of simulate a little bit the third term here. Can you see my mouse? I hope so. So you'll there is an attractive term on due to polarizability, and then a repulsion term when the atoms are very close by, and then you have standard Coulomb for charged molecule. So with this potential, which is kind of straightforward, not too complicated, you actually can describe protein in a quite good way. So over many years, these parameters here, K theta, Kb, Kphi, and so on, have been kind of optimized to represent well proteins. And this wasn't so difficult because you have only 20 amino acids, a set of limited type of interaction that you can make. So it was possible with this kind of potential to create molecular mechanics force field, which were quite accurate for protein. You could fold many proteins on short time scales just due to time scales alone. And so what are machine learning potentials? So this, if you want, is also machine learning potential. So it's a parametric one. So you have Kb, K theta that you're learning. They were learned once for all. There were some groups making this kind of fitting these parameters for all sorts of atom based on or structure based on quantum mechanics. And then they were releasing this potential. This was the previous way. And but it's very limited, no? So you add maybe 100 parameters only, 200 parameters, and the structural form of these parameters is very limited. It's also the many body terms of this potential is quite limited. We have 2 body, 3 body for angles, 4 body for torsion, 2 body again for Lennard-Jones, and 2 body again for charges. So any kind of correlation which is beyond 4 body, and really the majority of the interaction are just 2 bodies. So we are losing quite a bit of complexity compared to the quantum mechanical potential, which is many body. in this approximation, going from quantum to molecular mechanics. So what is a machine learning potential? Well, it's a potential of the form of E equal some sort of neural network, which depends of the coordinates on some parameters of the atom elements and the charges. R are the coordinates, Z are the elements, Q is the charges, potentially also spins. And we'll talk a little bit about that later on. And theta are just the learnable parameters. The neural network is differentiable. So if you have this as an energy function and you can differentiate not just for the parameters to optimize, but also for R. And if you differentiate for R, you can get forces. So by just learning this energy function, you can actually get forces on the atoms. There are some limitations, and in particular, neural network must respect some physical constraints. You cannot just have any neural network there. Historically, the way that this has been worked on, you could start from 3D coordinates, then some fixed vectorization. You could have graph neural network, transformers, spherical harmonics, and also delta learning when you actually do some quantum mechanics, like semi-empirical, and then you just use the neural network to fix this the difference between some accurate quantum mechanics and some less accurate quantum mechanics. And then you want to respect some physical constraints like translational, rotational, permutational invariance, energy conservation, and equivariance. And there were historically basically two types of potential, machine learning potential, parametric and non-parametric. So initially, actually, the non-parametric ones, so kernel methods, were mostly used. This largely grew out of material people more than biology people, because they had more problem. And in biology was easier. You just had 20 amino acids. There it was way more complicated in terms of atom elements. And they usually add very little simulations to run, and very because the quantum mechanics calculations are super expensive. So they were using non-parametric methods like kernel method. But these days, I think with the extra compute and larger data sets, it's actually everybody's probably using, or most people are using parametric method like neural networks. Okay, so all these methods are actually have started many years ago, and there were like a zoo of neural network potential over the years. And in this plot, I just show a few. So here on the right, on the legend, you see many methods up to a few years ago. And the plot shows on the x-axis, you have the number of training points that you used for each of these methods. And on the y-axis, you have the error on a test set that you get when you train on this amount of atoms. So for instance, let's say that we train on 1,000 points of this QM9 datasets. QM9 datasets is just a dataset of molecules where energy were computed for the ground state with some quantum level approximation. And there are 130,000 atoms in this dataset, so you could kind of take bigger chunks of the datasets and train on that, no? And if it's a property of statistical inference that you get this kind of a log-log plot, that the better you are, so you have this kind of lines, the more data you have, the lower is the error, and this kind of linear in a log-log plot. And the slope of the linearity and the position of this kind of curve depends on the methods. So if the star CM Coulomb matrix methods is the top on the right, and you see at 10K was able to give an error of 0.03 maybe electron volts. And then you have better and better methods if you go down, no? And then until like FG in this plot FGHL. I think at this point we are outside of the slide down here for the current methods. Yeah, so this is one of our methods that gets to 0.002, I think. But at this point, we got to a point that is actually not interesting anymore. Even the accuracy is just you get super accurate estimations of these energies. So we've been working on this area for quite a few years, and we created a lot of infrastructure for it, partially financed by the National Institutes of Health in US through the OpenMM project. So I'm one of the PI of OpenMM, which is molecular mechanics, molecular mechanics code. And our effort was, the effort of my group was mainly to introduce machine learning bits in this molecular mechanics code. So we had a bunch of infrastructure that we had to build in order to show you what I can show you towards the end of the presentation. You'll get this slide, so you get all these links to look at it later. Okay, so one of the first things we tried to do was to develop Cartesian tensor representation. So there were, as I show here, many featurization. You can have many featurizations. Some particularly effective methods are based on spherical harmonics. And we were always, spherical harmonics are totally fine. They are just, and they are okay probably for materials, but they are just too slow for biomolecular simulation. Biomolecular simulation, you need to be able to do billions of time steps to reach time scales which are interesting from a macromolecular perspective. And so you need you need some very fast method. And there is so much you can do when you use spherical harmonics in terms of speed. So we always focused on Cartesian tensor representation, and the first one that and also we always we start from the very beginning. We consider the equivariance, which essentially, if you rotate your system, you want, for instance, for forces, you want your forces to rotate the same way. This is not only valid for order 1 vector, like we also have the same kind of equivariance for higher order vectors. And are you there, by the way? I think I lost you. So I suppose we were here. So we're looking at Cartesian tensor representation because of speed concern. These speed concerns are not for everybody, like it's mainly for the biomolecular people that we have to run for billions of timestamps. The first work we did was to try to take an equivalent model, which was called PAIN, and kind of use the same equivalent kind of form, shape, and add some transformer. And we got state-of-the-art published. The paper was published in ICLR 2021. There is a source code which is called in the same way, TorchMD.net. This is much recent paper, more recent paper. I'll show you something about it later, so you don't need to write it down. Anyway, so again, this thing is the same as I said. You get in coordinates, put elements and charges, and then you have some kind of complicated convolution that spits out the energy and the gradients of the energy. Then this was good, but we were looking for being even faster or better. And so we started to work in this sort of framework where if we want to write, you can write a tensor X in these three by decomposing into these three parts: an identity part, an asymmetric and asymmetric part, and this transformed in a certain way that are well understood. So we can kind of learn parameters which are put in front of these terms, transforming X into X prime, and adding weights to these ones. So this is very simple formalism that we thought we didn't know how accurate it could be, but we thought it could be fast. And we got this sort of performance. Again, this is the same data set that I showed you before in QM9. So this is in milli electron volts now, not electron volts anymore. And this ET is the paper that I showed you before, equivalent transformer. And so we improved on this one, and we're also a little bit faster. The revised MD17 dataset is another dataset, in this case, of MD simulation by quantum mechanics. Here you have energy and forces and several molecules that you run the molecules with quantum mechanic calculations. And again, here is the TensorNet 2L. It's kind of the same as the other. All of these use spherical harmonics, all of this on the right. And we could also predict several quantity at the same times, including vector quantity. And again, we show that we have some state-of-the-art performance there. And what we cared the most was inference time. So with 0L means one interaction, zero interaction layer. So every atom just sees neighbors. 1L is just you also the neighbors see the neighbors again, and so on. So we went from 5 interaction layer to get good performance on with just 2 or 1, but even 0L, I think 1L gives already better performance than both the 5 layers and the 4 layers equivalent transformer. And the speed, though, was not as fast as we want to be. And we are working on an even faster method right now. But this is the method that we currently use in almost anything, this TensorNet. We're not using that much the equivalent transformer one. Okay, so I said for the code, you can have a presentation of all the codes in this preprint here, which is actually published now, but the preprint is there. And you can see how to install the code. There are several models, graph models, a transformer, the equivalent transformer model, and the TensorNet model. There are pre-trained models in some well-known data sets. There is training input examples and also work in a multi-node context, so you can kind of train over multiple GPUs and multiple GPUs over multiple nodes. And we spend a lot of time in optimizing the data loader for most data sets. It's super important for speed. There are examples of training examples, for instance, and then of course there are GitHub issues where you can get help in case you need it. So this is for the framework. So we use TorchMDNet for, it's based on PyTorch, and we use it for kind of everything is kind of our work environment. And it's pretty optimized, kind of well optimized. So you're supposed to get and used. So you're supposed to get a good if you want to use it, you'll get a good performance. Then we also spend, I didn't specify it here, but if you go in the paper, you can see it. We spend a lot of time in optimizing this from a software engineering perspective in terms of CUDA graphs, optimization, compiling, and so on and so forth, and all these, the PyTorch limitations. Okay, once we have this neural network potential, what do we do with it? And as I told you at the beginning, also we have this one super important problem that discovery is how to if you can calculate what's the free energy of binding between a protein and something else. In that case was a peptide. In this case, we're mostly looking at small molecule, drug-like molecule. And while for proteins, the normal molecular mechanics potential are pretty good because there are only 20 amino acids. For small molecule, that's not the case. No, the molecular space is kind of huge. It's very hard to build that simple potential that works for everything. And so our idea is that how can we use the neural network potential in a practical way? And there was this method, the chemical transfer method, which is a way to compute this free energy of binding between these two pairs. And it wasn't super well validated, so we made an effort to validate it over some standard data sets. And the reason why we used these methods is because compared to other traditional methods, computational methods to compute binding free energy like FEP, free energy perturbation, this one was very easy to adapt to machine learning potentials. So we actually only needs the forces as input. So it's, any kind of new force is easy to use it. So we validated here, and okay, and this is just an example. I'll show you a little bit. So over multiple data sets, we validated for multiple targets, and then you have kind of correlation of error in the bottom figures. And you can see that kind of different methods kind of all work more or less the same. There is not a big difference between one and the other. And which is what we wanted to see, no? We wanted to see if this method was kind of comparable to others. And what we did in this most recent paper is that we showed that we could use a neural network potential. Specifically, we were using ANI 2x here to see if we could improve this kind of correlation plots. So we see we went from the standard molecular mechanics potential on the left of this plot to much tighter correlation on the right if you use a scheme which was kind of designed to do neural network potential together with molecular mechanics. So we cannot still do the entire thing with neural network potential, but we can take the worst part in terms of molecular mechanics, which is the small molecule, treat that as neural network potential, and treat the rest of the system as normal as molecular mechanics. And even if you just do this simple change, you get quite a bit of improvement. In fact, probably you get state of the art already. And yeah, so we took 301 ligand paired, and then we do all the evaluations, and we got super accurate performance in terms. In these times we show the Kendall tau as a correlation, but also MIE. So you see that the blue is almost always lower. And this was kind of surprise because we only change the potential in a very limited way. So only for the conformational space of the ligand, but that's enough to produce this huge improvement. So this is a significant improvement. And again, okay, these comparisons of these methods, you get across the board much better performance, much better accuracy. We also use it in so we, why this is important. So if you get correlations like in TIC2 here, you can actually use it in a normal drug discovery cycle in a way that like it is kind of comparable to having experimental data. And that's what we do in Accelera. We essentially treat, we have an active learning loop, for which we take a subset of molecules, we build accurate data using these RBFE methods. We use this data as ground truth. We build machine learning model, then we can rank with this machine learning model much bigger systems, and we can do that in a kind of a filtering screening way or in a generative way. Actually, I'm not. Well, we also have recently published something in terms of generative, but I don't say anything in this area, and we only use the experiment as a way to validate this cycle, not in the critical path of the cycle. If we do that, this is kind of what you get. So we have this code, which is KDeep version 2, which KDeep was one of the, if not the first one, machine learning model to predict binding affinity from structure. I think KDeep and Atom-Wise were the first two ones, so it's quite old. Has been changing over the time. Now it's based on TensorNet, for instance. But so you get all this kind of, for each ligand, you get all this kind of predicted pKa and a standard deviation over that. And then with that, you can rank them. And when we compare our approach to, like, for instance, this reference here, these baselines, so, the blue line here with the number of ligands sampled, it's kind of the random baseline. So if you were doing random how many active compounds you find, the reference baselines is green is from this paper, and this is ours. No? So we get a lot better on the short amount of ligand, which is what we care the most. Okay, so so I showed you a little bit what is molecular mechanics. I showed you how you can go from quantum mechanics calculation to molecular mechanics kind of potential with this TensorNet and TensorConnet, and how you could actually use it in practice using this drug discovery kind of application for relative binding free energy. But the interesting part of this machine learning potential is like if you look at the past, not the past or the present even. No? So you have quantum mechanics, which is kind of Schrödinger equation, DFT approximations, and so on and so forth, which is kind of one world. Then you have molecular mechanics, which is another world, and then you have coarse-graining potential, where you maybe represent every amino acid as a single bit, for instance, and that was again a different world. So there are three fields which don't talk so much to each other, and actually machine learning unifies all of these. No, so it doesn't matter if you start from quantum mechanical data and you build a molecular mechanical potentials. It doesn't matter if you have a molecular mechanical potential for proteins, for instance, and then you build a coarse-grained potential where you only represent carbon alpha as 1 bit for each amino acid. You can use exactly the same machinery from a machine learning potential. That's a little bit connecting to what we're saying at the beginning. Is this the right language? And so what you do here is that you take a protein in water, for instance, and then you can do little simulations and then build a mapping. So you maybe remove the water and represent each amino acid as a bit. And you would like to have a potential which evolves this thing on the right, the coarse-grained system, much faster, but with the same kind of accuracy of the one on the left, which is what we're trying to do for molecular mechanics. We're trying not to run quantum mechanics, but we're trying to run this kind of molecular mechanics potential, trying to be as accurate as possible. And here is the same, but one level up. And we use this method, which is called force matching, because so we practically match the forces, because we can show that this learns a potential of mean force. And by learning a potential of mean force, you can specify what you mean by accurate coarse-grained potential. So previous coarse-grained potential in general, not all of them, were maybe a little bit heuristic. So how can I maintain this structure? How can we do that? And so on. But in this case, with this procedure, which is systematic, you can guarantee that the energy minimum are the same, for instance, because the potential mean force is transferred. And to demonstrate that, we took a data set of, we generated data sets of 9 milliseconds of protein folding, small proteins. These small proteins were shown to fold by death race in the past, and we just generating a lot of data for it so that we could train our potential. And then we did this coarse graining based only on carbon alpha. So we lose all the atoms. Now we have all the bits, and we run the dynamics, and we could show in this paper that we actually could recover all the structures. So you just now run these bits, and these bits reproduce the all atom simulations in to a large extent. So you see here, these are kind of RMSD plots, not that you can see that you explore folding, unfolding, folding, unfolding over our very short time scales because the system is coarse-grained. What you do when you coarse-grain, of course, you lose the kinetics. That's what you want to do because you want to be able to run these things faster. This is a kind of summary table, which maybe we can skip, but this paper was published in Nature Communication, I think. You can find all the details there. We recover with both a protein-specific model and a general model. We recover, we sample and recover the crystal structure for all of this. And more interesting is the energetics. So as I said, this method preserves the energetics. So if you see in the left, for instance, for NTL9, we have the above plot. The plot above is the reference all atom simulation, and the plot below is the coarse-grained one. In this two-dimension projection, and you see that we actually recovered all the minima. So you run the all atom, you run the coarse-grained, and then you actually reproduce the same important features. Not even just only the crystal structure, but also all the other structures. The same for protein G, similar plot. We try to generalize outside of the training set, and this had more limited means. So if, of course, we were only training on 12 proteins, so if we were using some mutation, we have some correlation, but not so much. Since then, we've done another paper, which is in the preprint archive, which is working a lot better in that respect, more general. And this is just an example of how it works. So you see this, you have only carbon alpha joint, and this is a simulation where, like you saw at the beginning, it forms a stable structure compatible with the crystal structure, and without any inputs. No, we don't say which part should be secondary structure, which part should be in contact or anything. Just physics. It just runs and it forms the correct structure. And again, the beauty here is that it's done exactly the same way that we did for the all atom methods. So from quantum to molecular mechanics, here we do from molecular mechanics to coarse-graining using exactly the same tooling, same machinery. Okay, so we go back here to quantum, and we probably need to re-up a little bit. So we are building now a machine learning potential, which is as accurate as possible for small molecules. So what do we need to do? We need to support charged molecules. It needs to be fast enough. We need to include all the biochemical relevant elements. It needs to be accurate for drug discovery. It needs to produce stable MD simulation. We also want all these elements that are here, and we took as molecules, we initially took all the PubChem molecules, and we kind of cleaned them up a little bit. We end up with around 100 million molecules. This is the initial data sets, initial smiles that we take. And if you do that, and you do that naively, you could have situation like here. So, you know, these two molecules, the top of the bottoms, are different molecules because of charge. And a lot of these methods, a lot of this neural network potential don't include charges or spin into their representation. So from a point of view, so they just include the coordinates and the elements. The elements, what elements they are, each atoms, and the coordinates of each atom. This is for like all the methods that I showed you before, maze and so on and so forth, Allegro, and also our method, TensorNet and Coherent Transformer. And you know what happens then? No, that these two systems are built from the point of, and of course the energy of the top of the bottom molecules here are totally different quantum mechanically because of the charges, and the configuration is different. But there is no kind of way like so much for the non-neutral potential to distinguish, because we don't provide the representation. We don't provide it as an input. We don't say this total charge is this one or spins are this ones. And the total quantum state is defined by the coordinates, elements, spin, and charges. So we should really do that. But no, most of the machine learning potential don't do that. There are a couple that do it, but they're super slow. So what happened if you do this? And then we started training, and what we saw is that we couldn't converge. And of course you can't converge because you have two molecules that are look identical to the neural network potential, but they produce totally different energies. So when you do supervised learning there, it's clearly that it doesn't work. So if you just take the top molecules here, you get super good accuracy. If you take just the bottom, you get super good accuracy. But if you mix them, then of course the accuracy is bad. So we did a modification of TensorNet, which include total charges and also spins, and in a very simple way. We can actually at zero cost. That was also important, at zero computational cost. And so now we can actually process this type of data sets without any problem, and we get same kind of accuracy if we take the top, if we take the bottom, or if we take the mix of the two. So problem solved. The important take-home message here: if you are going to use charge molecule in your training set, try to use a method which take charge into consideration, because otherwise you could have problems. At the moment, we are actually comparing also torsions, and torsions is like you take the molecule and then you torse, there are rotable bonds, and then you look at the energy across these rotable bonds, and then we are comparing how these compare between like kind of some sort of semi-empirical method, ANI, and our methods, and see how well we're doing. Okay, just this kind of offs, but I think it's interesting for a summer school. So we made a lot of effort in making available the tools in an easy way, not necessarily by expert for use, but also for anybody else. And so we have this open.playmolecule.org where we try to put any model or methods that runs in a reasonably fast way. We also spend a lot of time in writing a decent user interface for it in terms of graphics. You can actually even install this in your computer if it's Linux. And you have it's based on WebAssembly, so I can actually run Python inside the browser, and you can have Python systems here and do all sorts of type of filtering, representations, and change, and so on. And of course, you can visualize everything. And on top of that, you can save load sessions. You can also look at tabular data, and there are, as I said, the application like KDeep and so on, which runs relatively fast. We try to put them there, and so it's free. You just log in with your Google account and so on, and then you can access applications and try it. And it's an easy way to draw this documentation and so on. It's totally free. Okay, this is an example of how to use KDeep, for instance, to encrypt the scouts and another app. Thank you so much.
Amazing. I think we have a few minutes for questions. But yeah, if everyone wants to turn around to the camera and wave to Gianni again, thanks for being here and giving us the talk. All right.
Thank you. Thank you.
A few minutes for questions. So I'll go around with the microphone. Again, make sure you're speaking into the mic so he can hear you.
Hey, Yanni, thanks for the talk. It was really great. I had two questions for you. One of them was you were talking about how you made your force field kind of compatible with the QM and then the MM. So I'm wondering if your force field can be used with traditional force fields. You know, a lot of people have their force field of choice for modeling intrinsically disordered proteins or membrane proteins. So I'm wondering about the compatibility there. And then I can ask the second question after.
So the way that we approach the problem is that, okay, we have this very accurate potential because the accuracy of this potential is beyond needs. No? So there is more error in the FT that you are actually computing compared to like more accurate kind of couple cluster methods than the error that this machine learning potential produce. So what we were concerned though is the speed, no? So you have models with hundreds of thousands of parameters and a lot more calculation than molecular mechanics. And when we started with HMDNet, I think we were, if you were taking a small molecule, you were running that, we were 200 times lower than molecular mechanics. So what we did there was a simple trick. We just said, okay, we take everything molecular mechanics because we are not optimizing water, we're not optimizing proteins, but the small molecules the forces in the small molecules are computed with the neural network potential. So the intermolecular forces are all with the neural network potential, and the intramolecular, so between the small molecule and everything else, water and proteins, is done with molecular mechanics. This is still slower, but only 3-4 times slower than normal molecular mechanics, because now most of the system is still molecular mechanics, but we get the most value. So you can change with whatever force field you want. The only changes that it produces that the small molecule has dual representation. On one side, the forces are computed internally as neural network potentials and between atoms of different groups, so between atoms of proteins and small molecules, with whatever force field you have.
Great, thanks. And then my second question was with your Markov state models, like obviously, you know, you show that you preserve all the metastable states in your coarse-grained landscape. I'm wondering how much trust you have in the kinetics that you get from the Markov state model with the coarse-grained data from your force field versus the all atom.
It's a zero. No, it's not the kinetic. You want faster kinetics than what, otherwise there would be no point. So you actually want, you see that there we have folding in nanoseconds. For me, there are methods on which you can try to recover the kinetics, but for me, the point is not to recover the kinetics. You want much faster kinetics. Usually, the coarse-grained potential are way smoother than all atom potential. So all kinetics are 3 orders of magnitude faster. This allows you to see stuff that you will not be able to see normally with all atoms. Otherwise, you just run the all atoms. Yeah.
We have a few minutes left, so I'm going to ask everyone to just keep your questions to one question so we can get as many people in as possible.
Hi, thank you. I just wanted to ask a little bit on the coarse-grained procedure and so on. So basically, you're trying to learn some sort of hidden learning, hidden representation, right? How much training data do you actually need, and how transferable this actually is with respect to your new coarse-grained potentials?
So in this the paper that I showed you that is published, the transferability was minimal. So we were trying just to show that we could do it. So we could take like a force field trained on all these things, and the force field could recapitulate all these proteins. We have another paper which is in preprint archive that shows much better transferability, where it's trained on some cat data sets and peptide data sets, and then it shows that it can fold things which it hasn't seen in the data set. We have other work which will appear soon, which go even further. Does it fold anything? No. But every time we go a lot further than what we had before. I suggest you look at the other most recent paper on this, and there will be a couple more that will appear in the next few months.
Hi, I wanted to ask a question, I guess, related to transferability, but more thinking about to what extent can we think about being able to extrapolate potential? So thinking about training on a small data set, or sorry, a spatially small data, and then applying that to spatially larger data, or similarly training on shorter simulations and then applying that to larger simulations. Will that work? When does it work? When doesn't it work? That kind of thing.
Well, actually, the problem with transferability is the same. No, for coarse-graining and quantum is the same. No, you're training on some small subset of the quantum data, and then you're moving on to larger one and to a larger subset which you've never seen. So you want generalizability there, and the same is for coarse-graining. We have more experience for small molecules, and in small molecules it works pretty well to a large extent. There is the space is infinite practically, but you can kind of build a lot of you could do active learning cycle to try to say, okay, where do I have worse results, and then improve it. Dynamics is not usually a problem if you know how to create the data set. If you don't know how to create the data set, then of course is not like, let's say you take a more ground state molecules, then the poor machine learning potential never seen anything outside of ground state. As soon as you start the dynamics, everything blows up because you never seen anything beyond the ground state. So if you know how to build the potential, actually dynamics is not a problem at all. And so I'm pretty, I mean, I don't know, I'm positive.
Amazing. I think that's all the time we have for questions. Giving a great talk. If you didn't get it, yes, one more round of applause, please. Thank you.